Hello, my name is Adam Kollin. I'm the president of RHK Technology. I want to thank you for joining our webinar on R9's R9 Controller and its unmatched spectroscopy capabilities. We call this webinar See What You Were Missing for two reasons. First, if you're not familiar with R9 spectroscopy, today you will see what you were missing without it. You'll learn how you can advance your research significantly using R9's most versatile, powerful, and simple-to-use modes we call Perfect Spec. R9 and Perfect Spec provide results, insights, experimental freedom, and confidence that others cannot achieve. Now I'll show you what you've been missing without R9 and what R9's revolutionary Perfect Spec is waiting to deliver into your hands. The unique spectroscopic capabilities of the R9 are possible due to the unique design of R9's hardware, firmware, and software. The 24-bit dynamic range of the R9 allows optimal performance without the need to frequently fine-tune operating parameters. You'll be able to generate and detect more precise signals over a wider frequency range, opening the door to new measurement possibilities. A fully integrated system delivers lower noise, easier experimental configuration, and higher reliability and perfect synchronization between all functional blocks of the system. The noise floor of the R9 is far below that of other parts of the SPM experiment. The R9 will never be the limiting factor in your lab setup. R9's unique multi-speed data path allows sensitive measurements of low-level signals with a simultaneous acquisition of extremely high-speed signals. Other control systems lose the high-frequency information when they filter out their high-frequency noise. RHK's unique time-based data acquisition allows a deeper investigation into your data than is possible with controllers that discard the raw data once it's been averaged into pixels or spectroscopic curves. R9 has the perfect combination of ease of use for beginners with the ability to be customized and enhanced by advanced users. The unique architecture of the R9 connects a wide array of input and output signals directly to very large-scale field programmable gate arrays. These FPGAs contain the R9's PLLs, lock-in amplifiers, feedback loops, as well as the other firmware modules such as digital signal filters, scan generators, and the digital routing circuitry. One example of the advantage of the R9 approach can be seen in the configuration required to make DI/DV measurements. With the R9, it can be seen that the analog signal from the preamp is only digitized once. From that point, the signal travels through the R9 as digital data. This digital data feeds the feedback loop in both lock-in amplifiers. The current, topographic, and lock-in signals maintain their full 32-bit precision and are stored directly without ever being converted to analog signals again. In contrast, using an external lock-in amplifier, the data undergoes numerous conversions from analog to digital, then back to analog, then back to digital, before finally being imaged and stored. In addition to the noise generated by the extra cables and connections, much precision is lost in the needless data conversions. RHK's patented Iconic Hardware Description Language, or IHDL for short, allows easy configuration and optimization for any type of experiment. Since all signal handling is performed in the digital domain, the noise level is reduced to the theoretical minimum. The spider's web of cables that connect the multiple modules required by traditional control systems are completely eliminated. In addition to configuring the R9 hardware, IHDL also allows the user to quickly expand and modify the measurement modes and procedures. Minimal time is required to learn IHDL compared to other programming languages. Many researchers limit their research due to the limited capabilities of their tools. If your controller has a low analog bandwidth and digital sampling rate, you do not consider making time-resolved measurements. If you only have one lock-in amplifier, you do not consider multi-frequency excitation and higher harmonic detection. The R9 allows you to work with signals from microvolts to volts, from DC to 20 megahertz. You're only limited by your imagination. In most cases, the most difficult part is thinking outside of the box to imagine a potential new measurement mode. Implementing that new mode is the easy part with the R9's patented hardware and procedural graphical building blocks. One of the truly unique capabilities of the R9 is the ability to have such low noise and resolution while maintaining extremely wide bandwidth and timing resolution. As you can see from the graph on the left, the input noise of the R9 is far below the noise floor of any experiment. The R9 will never be the limiting factor for your measurements. The low noise of the controller, coupled with the high resolution of the input and output stages, allow signals as small as a few microvolts to be generated and measured, as shown in the graph on the right. R9's wide bandwidth and sampling speeds allow extremely high-speed signals to be accurately measured, such as higher harmonics of oscillating probes or transient signals as short as 10 nanoseconds. This slide shows the individual oscillations of a tuning fork-based AFM as it approaches and then crashes into the surface. The 100 MHz sampling rate allows the individual oscillations in the crash event to be studied. The graph on the right shows the excitation of higher eigenmodes of the tuning fork due to the forces exerted during the probe's approach to the surface. As can be seen, the higher eigenmodes dampen out within 6 oscillation cycles. As this high-speed data can be exported, an FFT analysis could illuminate which eigenmodes had been excited. This data is zoomed in from the data shown on the left. One of the most praised features of the R9 is its unique user interface. The GUI can be quickly configured for beginning students, so they're presented with a limited set of controls, allowing them to quickly learn how to operate an SPM and to begin obtaining results with minimum delay. The GUI can then be adapted to the user's growing needs by exposing additional controls to provide a deeper level of control over every aspect of the microscope's operation. In the example shown, the parameters for the feedback loop are first limited to the set point and integral gain. With a few clicks of the mouse, the feedback type, proportional gain, and tip controls can be exposed for the more advanced user. To prevent the user from accidentally setting parameters to values that would cause unstable operation, safe ranges can be selected that will avoid crashing a probe or lead to violent oscillations of the piezo tube. This safety net is available for almost every parameter in the R9. When I showed this to one customer, he laughed and told me that if he had $1 for every time his students crashed a tip due to setting the bias or set point to 0, he'd have already paid for an R9. As you can see, the parameter changes to a green background to remind you that you have limited its range. The R9 control system allows the user to perform any type of topographic and spectroscopic measurement. The R9 allows any number of parameters to be ramped or modulated, such as the bias voltage, feedback set point, Z position, or magnetic field, and then plotted against any number of responsive signals. These signals can be read from external sources, such as an STM or AFM preamplifier and photon counters, or from internally calculated signals, such as the lock-in's amplitude and phase, the PLL's frequency shift and dissipation, Z position, and so forth. As the R9 contains multiple lock-ins and PLLs, over 60 channels of data are available to be acquired. RHK's data acquisition is a new concept in data acquisition based on the idea of big data that we call time-based data acquisition. Time-based data acquisition allows you to dig deeper into your data to find new correlations or more subtle results that are lost using typical acquisition methodologies. Time-based data acquisition also provides a unique tool to help optimize your operating parameters, especially the multiple parameters involved in spectroscopic acquisition. We give you new windows to visualize the data that is ignored or discarded with every other control system. Time-based data acquisition also records all changes to your acquisition parameters during measurement, so the exact environment is always known at every pixel on an image and every point on a spectroscopic curve. These parameter changes are stored with the data and are shown on the images. Mousing over the dots will display the changed parameter at that point. The R9 control system allows the user complete control over every aspect of spectroscopic measurements. This includes the ability to control exactly where on an image a spectroscopic measurement has been acquired. Competing control systems often lack this capability. They typically first acquire a topographic image and then scan a second pass to make spectroscopic measurements. The time delay between these measurements adds an uncertainty as to the exact location of where the spectroscopic measurement was acquired. For example, when you click the mouse on an image to make a spectroscopic measurement, the tip must move from the current location to the clicked location. Unfortunately, the location of the measurement is likely not the exact location of where the mouse was clicked. Due to piezo creep, hysteresis, and thermal drift, there is a zone of uncertainty where the spectroscopic measurement was actually made. But there is a better way, and that is to acquire the spectroscopic data simultaneously with the topographic data. This completely eliminates the zone of uncertainty and always provides the exact position of spectroscopic measurements. In addition to the wide variety of spectroscopic measurements that can be performed, R9 provides complete flexibility of where these measurements are made. There's a trade-off between the number of spectroscopic measurements to be acquired and the time for the measurements to be made. RHK provides many methods to choose locations for spectroscopic measurements to provide the maximum amount of data in the minimum amount of time. Efficient data collection allows more measurements to be made per day, speeds the time to publication, as well as helps save on the cost of liquid helium. In this example, spectroscopic measurements are performed at a grid of points acquired simultaneously with the topographic scan. The grid is spaced evenly across the image. Any density of grid can be selected from 4x4 points up to 1024 by 1024 points. In this and all following examples, the spectroscopic measurements are stored with the topographic data, maintaining the correlation between the topographic and spectroscopic data. The second example shows the region mode. This mode allows a grid of points to be defined over any subregion of the image. This is useful when the desired spectroscopic information is limited to a portion of the reference image. Here you can see the simultaneous topographic and spectroscopic data being acquired and displayed in real time. The third example shows the line mode of selecting points. A line can be drawn over any features of interest. When the probe crosses a defined point during the next topographic scan, the scan will stop and the spectroscopic measurement will be performed. The number of points on the defined line can range from 2 up to 512. The fourth method of selecting spectroscopic locations is the interactive method. In this case, the user can click on any number of points on the reference image. The probe will stop at each of these points during the next topographic scan to collect the spectroscopic data. The fifth method of selecting spectroscopic locations is to choose the points after the topographic scan has already started. This works for large features where you can see from a few scan lines before the desired location. Clicking at any point on the image ahead of the probe will cause the scan to stop when it reaches that point to make the spectroscopic measurement. Many points can be selected this way during the scan. The sixth method of selecting spectroscopic points we call spec along a line. A line is drawn on the reference image, and the number of points to be acquired is defined. However, instead of rescanning the entire image, the tip scans along the line 4 times, both before and after the spectroscopic measurements are made, to create a pseudo 2D image. This quickly shows the exact position of the spectroscopic measurements in relation to the features on the surface, something that is not possible when the spectroscopic and topographic measurements are not taken at the same time. The position of the spectroscopic measurement is directly shown on the topographic image. Once the locations of the spectroscopic measurements have been defined, the R9 allows an almost unlimited amount of data to be acquired. As been shown, the spectroscopic measurements can be made at up to 1 million locations on an image. Any number of curves can be acquired at each location, and any number of points can be acquired on each curve. And multiple channels of data can be acquired at each point. The upcoming 64-bit version will allow even larger amounts of spectroscopic data to be acquired. This really is big data. Once large arrays of spectroscopic data have been collected, Various types of analysis are possible. In this example, curves at the specific locations are selected for analysis. In this next example, the data array is sliced according to the bias voltage to create current images. RHK's data format is open, so users can import their data into their LabVIEW or MATLAB programs for detailed analysis. One of the unique design concepts of the R9 is our method of data acquisition. Since the first STMs were developed, most researchers have dealt with their data as pixels. Though this is a convenient way to visualize data, the world is not made out of pixels. The real world is analog. Real information can be lost when converting from an analog signal to pixels. RHK looks at an SPM experiment as a constantly changing interaction between a probe and a sample, with various sources of excitation and various channels of responding signals. The data is processed down to discrete pixels for visualization, but the raw data can be maintained for future investigations. R9's time-based data acquisition can be even more useful for spectroscopic measurements. The data stream for the various channels of data is acquired continuously during an experiment. It is not interrupted between the topographic and spectroscopic portions of the measurements. With the R9 controller, in addition to seeing the data as a single data point at each bias voltage step, you can dig deeper. You can visualize the current after you stop scanning and before you open the feedback loop. You can visualize the current as the bias voltage is ramped to the starting value of the measurement. You can visualize the amount of overshoot at each step. You can see each individual reading at each step. All of this information can provide new insights into your experiment. It is also an excellent tool to help optimize the various settings of the measurement. Other controllers turn off their data acquisition during these phases of the measurement and throw away the raw data after it's averaged for display. Everyone is familiar with the concept of a spectroscopic measurement. You ramp the bias voltage and measure the current. It sounds easy, but real life is never that easy. It gets more complicated when you have to take into account the complex interaction between the probe and sample. It's no wonder that most people just guess at the settings and never go back to try to optimize them. If you don't have good tools to help you optimize the settings, you probably won't take the time to do it. But this can be a serious mistake. At a minimum, incorrect settings will waste valuable research time. In the worst case, incorrect settings will allow artifacts to distort your data. In this slide, you can see the differences between the idealized and the real-world current measurements. The black bars on the graph represent the data you expected to get. The gold bars represent the data you actually got. The length of the bars is the amount of time you sampled at each bias voltage. You can see there is a significant deviation between the idealized and the real current. Plots made from this data would not be accurate or repeatable. The amount of error is a function of the settings on the parameter panels. To reduce the error, you can guess at the settings, but it's a slow trial and error process that is difficult to optimize. Competitive control solutions simply do not provide the tools to improve the process. Since they only gather data at a subset of points, you are working blindly. R9's Perfect Spec technology provides the tools to easily visualize the entire spectroscopic process. Since we acquire the entire time trace of the current during the spectroscopic measurement, it's straightforward to adjust the parameters to minimize the errors and artifacts of the measurement. The purple bars in the graph represent which subset of the acquired data can be selected for artifact-free measurements. Many spectroscopic measurements require a lot of data to obtain the desired level of signal-to-noise. It is most convenient if this can be done in a single spectroscopic suite, but the long acquisition times often make this impractical. As the feedback loop is usually frozen during this time, even small amounts of thermal drift can distort the measurement. The measurement is therefore broken into a series of shorter measurements that are averaged together. The problem with that approach is that if the gap conditions are not exactly the same each time the gap is stabilized, the probe will be at a different height above the surface during each measurement, and the resulting data will not be reproducible. This problem can be quite severe. Most controllers use the same feedback loop parameters to stabilize the gap as they use for topographic scanning. The noise in the tunnel current causes variation in the Z position. This is made worse since the bias voltage is often also being modulated. Each time the feedback loop is frozen, there can be a large variation in the Z position above the surface. Therefore, the gap resistance can be different for each curve. Many curves need to be averaged to try to remove this variation. This wastes precious time and helium and causes broadening of spectroscopic features. But there is a better way. The R9 system incorporates unique hardware and software capabilities which allow the user to quickly and easily optimize the settings of the spectroscopic measurement to provide highly repeatable measurements. This capability delivers greatly increased productivity as less data is required to provide high signal-to-noise results. More productivity means more results in less time with less resources, such as liquid helium. The R9 acquisition procedures provide the user the ability to perfectly match the gap characteristics to their individual requirements. We call this Perfect Spec. Since the optimum gap parameters for topographic and spectroscopic measurements can be very different, R9 allows these two sets of parameters to be configured separately. In this example, we show that the feedback loop is set with a 1 kHz bandwidth during the topographic portion of the measurement to allow the probe to quickly scan over the surface without running into surface features. During the topographic portion of the image, the bias modulation is turned off. Once the probe has reached the position for a spectroscopic measurement, the gap can now be optimized for the measurement. First, the bias voltage and set point can be changed to a value that is appropriate for the spectroscopic measurement. The feedback bandwidth is then reduced to eliminate any noise in the Z position. The feedback loop is then frozen. Finally, the bias modulation is turned on. As you can see from the graphs, the variation of the Z position between multiple curves acquired at a single point are much less than what is possible with other control solutions. This provides for greatly improved repeatability between the curves. In addition to being able to optimize how each portion of the measurement is made, R9 allows you to visualize portions of the experiment that are not even acquired by other controllers. This can help you gain a deeper understanding of the measurement process and help visualize conditions that cause artifacts in your data. The old sayings, "what you don't know can't hurt you," or "ignorance is bliss," do not apply to experimental science. In this example, we show the data acquired in ramping from the bias voltage used for scanning to the start point of a spectroscopic measurement. Other controllers simply assume nothing interesting is happening there, so they do not bother to collect that data. However, the rate that you ramp the bias voltage can easily desorb molecules off the probe, so watching the stability of the signal as you ramp it can help optimize the speed you set this parameter. These next slides help to better visualize how Perfect Spec can help you optimize the parameters for your spectroscopic measurements. This slide starts with the tip in position before the spectroscopic measurement is performed. The feedback loop is set to its topographic parameter set. The R9 now switches to the feedback loop spectroscopic parameter set. In this case, the bias voltage, current set point, and feedback loop bandwidth have been modified. In the next step, the feedback loop is frozen, the bias modulation is turned on, and the bias is ramped to the starting voltage of the spectroscopic measurement. A delay has been programmed to allow transients from this ramp to decay before the measurement is started. The spectroscopic measurement is now performed using the parameter set in the dashboard controls. Depending on which options are selected in the menu, more spectroscopic curves can be acquired, or the controller can now switch back to topographic mode and the probe can scan to the next spectroscopic location. In the example shown, the feedback loop was switched back to the topographic parameter set. The R9 controller allows fast and easy modification to both the hardware and software configurations. We provide the tools to make any type of spectroscopic measurement. We also provide the tools to visualize the data in a way to allow you to fully optimize the parameters. The ability to change the feedback loop settings before spectroscopic measurements was suggested by a user as his existing controller did not have this capability. It only took about an hour to implement this feature. With the R9, coming up with new ideas is the hard part. Implementing them is the easy part. Having a tool that allows you to dream of new measurement modes can help propel your research to the top. Here is a comment from one of our users. A variety of the pre-programmed measurement modes will now be shown. These are only the choices that we have thought of. The modes that you make are only limited by your imagination. All of these spectroscopic modes can be acquired in the single point mode, in a grid, along a line, interactively defined, and so forth. Each spectroscopic mode has its own parameter panel. The values are all in physical units that match the measurement mode. The first mode is standard IV spectroscopy. The second mode is DIDV. The parameter panel is shown with the basic menu options available to the user. Clicking on the top right corner of the panel opens a menu to allow the user to select which parameters will be shown on the panel. The parameter panel now exposes many of the controls that would be useful for the expert user. One parameter that should be reset each time the tip or sample is changed is the phase offset of the lock-in amplifier. The phase offset function allows the lock-in amplifier to automatically remove the artifact in the tunnel current caused by the capacitive coupling of the tip and sample. Without the proper setting of the phase offset, the DIDV measurement will be highly distorted. The R9 makes the optimal setting of the phase offset fast and easy while providing an excellent visual understanding of the process. When the phase offset button is pressed, the probe is retracted a small distance from the surface, so all measured current will be due to the capacitive coupling of the tip and sample. The bias voltage modulation is turned on, and the phase offset of the lock-in is rotated from 0 to 360 degrees. This data is plotted in real time. You'll be able to see where the current is at its maximum positive and negative values, as well as where it crosses 0. Pressing the Find Peak button will select the maximum positive value on the curve. Now pressing the Select Offset button will subtract 90 degrees from this value, which will remove the effects of the capacitive coupling. Finally, pressing the Set Phase button will enter this value into the lock-in amplifier. The bias modulation is then turned off, and the feedback loop is turned back on, so the tip will return to its imaging position. The DIDV spectroscopic measurements can then be made. This data was provided to us by Dr. Ray Chudhuri. He was our very first R9 customer. Dr. Ray Chudhuri suggested that we modify our spectroscopic procedure to turn off the bias modulation when stabilizing the gap between spectroscopic measurements at each point. The improvement from this modification greatly reduced the number of curves required at each point to achieve his desired signal-to-noise. With the reduced time at each point, he was able to increase his maximum data array size from 32 by 32 points to 64 by 64 points before his helium-3 system needed to be regenerated. Dr. Shi had been unable to resolve the subtle spectroscopic feature of his sample with our competitor's controller due to the higher noise level of their circuitry. He also complained the controller's internal lock-in amplifier added significant artifacts to their spectroscopic and topographic measurements. With 1 day of receiving our R9, he was able to obtain this result. Obtaining the second derivative of the tunnel current is as easy as turning on the second lock-in amplifier inside of the R9. No additional cables or connections are required. IZ spectroscopy is configured just like any other spectroscopic mode. Just set the appropriate parameters in the menu and start measuring. As always, no additional cables or connections are required. R9 comes with convenient spectroscopic visualization tools. 4 different signals can be displayed simultaneously. Up to 512 curves can be displayed inside of each graph window. In addition to displaying raw data, various processing options can be utilized in real time, such as smoothing, first and second numerical differentiation, as well as integral. Once the spectroscopic data has been acquired during the topographic scan, you can graphically select any individual spectroscopic measurement, or you can select all of the curves acquired within a defined region. Both the topographic and spectroscopic data is stored in the same data file, so the data always remains correlated. RHK has now sold 200 R9 systems. We still maintain a large staff dedicated to its continued refinement. The need for technological innovation never stops, and we will continue to develop the R9 to assure it remains the most technologically advanced control system available. We appreciate the time that you've taken to see the R9 and its unique Perfect Spec in action. Today you've learned about the superior results and data you will obtain from R9's Perfect Spec and its multiple modes of spectroscopy data capture, the special insights that only R9's time-based data acquisition can provide, R9's ultra-fast data capture, as well as the many other unique features and capabilities of the R9 system. Please feel free to contact RHK for more technical or sales discussions about our R9. Well, we appreciate the time that you've taken. If anyone has any questions after having seen our presentation, please type it now into the question window. I have a question: how would I set up to image with Q+ for topography but do DI/DV spectroscopy? With the R9 system, we have many different channels of data that can be acquired, so it's absolutely no problem to image in STM mode and do AFM type spectroscopic measurements, or to feedback off of AFM for the topographic and switch to, as you then freeze the feedback, to make STM measurements, whether it's IV or DI/DV.
Yeah, in this case, this is Kenneth Kollin. I'm the product manager of the R9. I'd also like to send my thanks to you for watching the webinar. And as the current is just another data channel that's coming up while you're doing your Q+ for feedback, all you have to do is freeze the feedback and ramp the bias, and the current is being collected.
What's the maximum number of points per curve?
Well, that question depends on what sort of curve we're doing. If we're doing a point spectroscopy, you can have very many points. If you're doing a grid spectroscopy, then the number of points will be divided by the number of pixel locations. We can check on what the number of points can be, but I believe it's quite high.
And the single point would certainly be in the tens of thousands, if not hundreds of thousands of points, being that we have resolution really down to the microvolts. But if you're taking 100,000 points on a curve, you probably wouldn't have that many if you'd taken 1 million curves. But that's not a question. I don't think we've ever gotten a complaint that there's an upper limit to how much spectroscopic data can be acquired.
Now, this is speaking with the way the software is right now. Currently, the software runs as a 32-bit application. However, we're in the process of testing our 64-bit application, which will have basically a limitless amount of points per curve that you could take, since you're no longer limited by the 4 GB memory that Windows allows a 32-bit application to have.
Okay, we have a question. With time-based data acquisition, can the spectroscopic data be reanalyzed in post-processing to avoid or correct for artifacts? One nice thing about the time-based data acquisition, when you acquire, you're acquiring a lot more data than what you're seeing on the IV curves as they're being displayed. As we showed in earlier slides, we just pick a subset of the acquired data to show. So when you open up what we call the history, you see the entire time spec, and you'll see the parts that were cut out that were used for the actual visualization. For instance, after you made a bias voltage step, you might wait 1 millivolt before you start using that data. Other controllers wouldn't acquire data for that first millisecond. But you might see that the transient had not yet decayed, so you could then, instead of waiting a millisecond, say, wait 2 milliseconds, and then just acquire the rest of the data before you make a step. Or you might have said, I didn't need to wait that first millisecond, let's include more of the data, not less of it.
So if you've enabled the raw data to be saved, there are menu options to let you decide to save all of the raw data or portions of the raw data or none of the raw data. It's really up to how you want to utilize the system.
And that is a very good question. This is actually something we've been discussing, that specific autocorrection for the Perfect Spec Phase 2.
Well, we have another question here. There were many STM examples. How are the corresponding AFM measurements made?
Okay, I'd like to answer that one. A spectroscopic measurement is little more than changing a specific type of excitation and recording the result. So there's really no actual difference between doing an AFM or an STM type spectroscopic measurement, meaning you're freezing the feedback, for example, and ramping another signal like the Z position or the bias while recording the input signals. So it's really quite the same thing from the controller standpoint.
So you could ramp really any signal. You can ramp the bias voltage, you could ramp the frequency, you could ramp the Z position, you could ramp multiple signals at once. It doesn't have to be a single excitation. And then you can record any number of data. Had you been feeding back off of AFM, you can still do STM measurements as long as you had a conductive tip.
Okay, on programming in the LabVIEW-like window, can the software check whether the program is written safely without hardware-software crash? Yes, actually. Yeah, when you're using our external control interface, or the Inventor SDK as we call it, whenever you send a command to the R9 to make a modification, it sends a response back to the sender to let you know that it has actually successfully done that. So whether you're starting a procedure, it will let you know when the procedure is finished. If you're trying to ramp a value, it lets you know when the value has finished ramping. If you set a value, it lets you know that the value has been set. So you do get a response back to let you know that things have happened.
If you happen to send an illegal command, you just mistype, the syntax, it'll simply ignore it.
And it will tell you that your syntax is incorrect. Or if you're trying to change, another example, something that's set to read only, it will tell you that that's illegal, you can't change that. Also, if you try to set a value that's outside of the legal range of values, for example, you try to set the bias to 100 volts and you only have a 10 volt bias, it will let you know that you just tried to set a value that's out of range.
Now that's using the external command interface. Using the internal commands, the IHDLs that was showed in the webinar, before you can run any procedure, it will auto-verify, and it will either come up and say that procedure is okay to run, or it'll say you made a mistake, and it'll point you to where you made the mistake. Likewise, when you're configuring the hardware, it will not let you start up if you've made illegal connections. It'll only allow connections that will work correctly. Okay, well, if we don't have any more questions, we appreciate your time. We're certainly always available by email, by phone, to talk to us either directly or through any of our international distributors if you have any more questions. Okay, thank you for your time, and we look forward to further comments and hopefully some orders for the R9 controller. Thank you very much.